Hey guys, how are you? Okay, and we have sound. Good. Wow, everyone's coming in. The semester is almost over. I guess that means there are exams soon. So the next exam is going to be on next week, Friday. So it's not next time, but it's next week, Friday. And then I think we have a week with no exam, and then that's the last week. And then we'll have the final exam afterwards, sometime much later. All right. Well, we're at that time of the semester where you can feel the end. And from my point of view, that means that we need to cover a bunch of interesting topics to make sure we wrap up this semester nicely. Okay. Well, let's continue from where we were last time. We were talking about these proofer codes, right? And what we had shown last time is that there's a way that you can take a tree and you can make a really thin strip of numbers that will encode everything about that tree. So last time we talked about the proofer code. And the concept of the proofer code was actually really simple. You just keep finding the smallest leaf and taking it away. Keep deleting the smallest leaf, right? And you take it away and removing it with its edge. Keep deleting the smallest leaf with its edge. And we were just recording down, what is that smallest leaf? And we were actually recording down the neighbor, its neighbor. We were always writing that down. So we write down its neighbor. I'm remembering that we're only doing this like bottom strip of the proofer code because we also kind of ignored the last one, right? The very last one, the neighbor is always n, the largest vertex. But ignore the last writing since it's always n. Okay, and let's do an example of let's do an example of a decoding. Try decoding. Okay, so what that would look like is suppose somebody gave you a proofer code which was just here we have this thing, and let's just make up something like 3 7. Oh no, 7's scary. Might be too big. I'm going to write some smaller. Well, maybe it's not that big, but let's just write some smaller numbers anyway. 3 6 1 1 2 5 4. I don't know. 7. Okay, let's see. Suppose that was it. First thing I want to ask is, could this be a legit proofer code? Today we're kind of thinking of like how you go about going backwards, how you go about reconstructing what the tree is from the code that you have, because the deep question we're going to be talking about today is that miraculously every possible strip of numbers somehow can be back recovered and it's always a tree. That's actually how we're going to get the n to the n minus 2. So if this was here, first of all, is there a notion of, remember I was being careful as I was writing down numbers? Would there be anything that would make you very scared and be like, oh no, that's not a legit code? I mean, if I wrote down numbers and I wrote down -5, you'd be like, that's bogus. You can't have that. If I wrote down pi, you'd also be like, that's bogus. But there's another kind of thing that would be bogus if I wrote down a strip of 8 numbers. What else could possibly be bogus if I wrote a strip of 8 numbers? Braden.
If you have a node number that's too large, like if you have like a 20 in there.
Yeah. I don't really like these plus minus ones things. I'm always off by 1 when I analyze stuff, but I'm like 20, that's clearly too big. You should not get a 20 because remember, from this you actually know what n is. If this was the strip you wrote down, you know that this has how many numbers in it in terms of n? Does anyone remember or know? Remember, we're going to write down everything, but we'll ignore the last thing, which would have been just an n. So here is this proofer code, which, remember, the last thing has been ripped off. What is n here? I have 8 numbers written down. How many vertices are there in the tree that supposedly made this? Basically, if n is the number of vertices, how long is this strip? Chris.
There are 9 vertices.
There are 9 vertices. So how did you get the 9?
So you know that the last one is always going to be whatever's left to be
Right.
number. So you know that there's like, and then we excluded that, so it's 8 plus 1.
Okay, so now here's the thing I wanted to double check. So it's like, yes, there should be 9 things when I write it down. There should be 9 total columns in the end. But how many vertices would that be? 10. Yes, that would be 9 edges, right? That's okay. There would be 9 total columns, which is 9 edges, but that gives you 10 vertices. So the important thing here is that the number of things I wrote down is always n minus 2. So I'm just going to write down this thing. You end up writing n minus 2 numbers. Okay, that's actually kind of satisfying, by the way, because where are we getting the n to the n minus 2 from? Well, I have n minus 2 numbers, and each of them is 1 up to n. So in some sense, I could actually write numbers all the way from 1 up to n inside here. You can have the biggest vertex appear as the attached neighbor of some leaf. That's possible. Actually, before we try decoding this, I want to try decoding a simpler one. So let's pause on that one first, and let's try another one. Or try, what if we have 9, 9, 9, 9, 9, 9, 9, 7 nines. Let's do that one first. What would that be? How do I decode that in the sense of like, what did that come from? What tree corresponds to this proof or code? Anyone help me with this? Andrew.
Something like 9 in the middle of all the other ones.
Okay, so let's finish this up first, though. You're right. It's 9 in the middle and everything else sticking off. But like, what number should be there? We just did this, right? So that if I have 7 numbers written down, then I know that n equals, so n minus 2 is equal to 7 because I have 7 numbers written down. Therefore, this guy is also 9 because that's n. And, well, what's the top going to be? Actually, that's kind of neat. You already found out that you just have all the things where the thing they're attached to is the 9. You can already see that the way that this graph would look is like all this stuff. If I could count, 1, 2, 3, 4. That was supposed to be a 4. 4, 5, 6, 7, 8. I can't count. So let's erase this thing. Okay, 8. Right. So that's actually exactly what this graph is. It's very, very satisfying that you could sort of see it come from something. But what would the top look like? Let's remember the decoding algorithm. What would be the top exactly in order as we go across the top, and why? Like, how do you figure out the first one again? Do you remember? Right, if I want to decode this thing, what's the first thing that happens? What do I put here? Aaron.
The smallest thing that's not on the bottom row.
Yes. You just exclude the bottom row, and you look for the smallest thing that's not there. So the smallest thing among 1, 2, 3, 4, 5, 6, 7, 8, 9 that's not there is 1. And then when I want to know what's next to the 1, this is the first general step. Well, how do I figure out what to put there? What do I exclude? Andrew.
You exclude everything to the left and then everything that's down to the right.
Yep, you always exclude the left and below it to the right, so you have to exclude 1 and 9, so that's 2. And you can see this is beautiful because always the next one will be exclude the stuff to the left, so exclude 1 and 2, and also exclude the 9, so that would be 3. And it just keeps going 4, 5, 6, 7, and 8. And that's actually the extended proof or code of this particular tree, where once you have this large table which has 2 rows and n minus 1 columns, you're just like, let's just make the graph where I connect the things that are above each other. Every time I've stacked numbers, I just go and make an edge there. Okay, now let's try decoding this other thing. This more sophisticated, totally random thing that we drew. So what do we do here? I'll do the first step, which is I know what the last thing is. We figured out this has 10 vertices, and so the last thing is going to be a 10. But now, how do I do the top row? Can people help me with that? You can just like type the number in also if you want. You can just type the number in the chat. It's like, just, I guess we could sort of do it together. It's like what goes here is just like, what is the smallest thing not there? Sydney says 8. Do I believe 8? Looks legit. That's 8. Okay. That's 8. The next thing is, now I go here and I'm like, the smallest thing that is not 8 and not 611 blah 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 blah. What's that? That's now 3. It's actually kind of nice. You can sort of see that it's 3 because it was 8 was the smallest before, but now 3 is not one of the ones you ruled out. Okay, now rule out 8, 3, and also the ones. I'm guessing it's 6 is next. Okay, 6. Okay, and now the next thing is I need to rule out 8, 3, 6, as well as 1, 2, 5, 4, 7. 1, 2, 3, 4, 5, 6, 7, 8. Is it 9? 9. Okay, 9. Now what happens next? You can sort of see what will happen next. It's like there's no more 1s on the bottom, so now I have no more reason that I had to rule out 1, so it's going to be 1 next, right? I always want the smallest thing that's not on the top or below to the right, and now I don't have 1 included there anymore to avoid, so it's 1. And I'm just like executing the algorithm in my head. The next one is like anything up there, anything not up there, and also not 5, 4, 7, whatever, it should be 2. 2 is the next one. By the way, if I make a mistake, just like tell me, because that might happen. So the next thing is like, suppose I want to block out these things with the 2, I also block out 4, 7, and 10. The way I'm looking at it is like, well, probably 5, because that looks like I have no more reason to block 5. Okay. And then the next one's probably going to be 4. And then the next one after that's probably going to be 7. Okay. So I've just gone and decoded this thing, where the way I decoded, my decoding algorithm was just take the smallest thing that's not excluded by the left and by the bottom to the right. And you got this. Now the question is, what does this even look like? Let's draw this thing. Well, 8's connected to 3. 3 is connected to 6. 6 is connected to 1. Okay. 8. Well, oh, nice. It's just kind of chained together. But then 9 is connected to 1. All right. 1 is connected to 2. 2 is connected to 5. 5 is connected to 4. 4 is connected to 7. Wow, what a weird tree. Okay. Did I make a mistake? I think it's okay. Okay, I think it's right. So we just made a tree which is like almost like one long path with just something sticking out. But I guess that's a happy coincidence because it shows you can have two very different kinds of trees. One is like everything all smashed together in the middle, and the other is it decides to kind of like walk along lazily. Yeah, it's proportional to the number of repeats on the bottom. Oh, yes! Actually, you're right. Chris, that's good. You're right. Actually, the number of repeats on the bottom is very related to this. This is good. This is good. I did not think of explaining that to you guys. Somehow really needs to change that. Yes. Wait, BST? Yeah, breadth first search tree or something like, yeah. Okay, cool. But so what we just saw is that you can somehow decode these things. But the reason I went and did this is because if somebody just gave you a table with 2 rows, there's no guarantee that's a tree, by the way. What I'm trying to emphasize is we actually showed last time. Let me write down what we showed last time. Last time we showed something very exciting. Last time, what we showed is that there's a way to encode a labeled n-vertex tree as a strip of numbers n minus 2 long, and each number is something between 1 and n. So there's a way to do this encoding, but it has a special property where if somebody just gave you that strip, you can know exactly which legit input went in, such that no 2 legit inputs, i.e. trees, make the same output. Is that okay to people? Like, that's what we were really emphasizing last time. We were like, here's the encoding algorithm. You go and make this long thing with 2 rows. Here's how you strip it down. But if I started with something legit and I followed all of my rules, the thing after you strip down, there's a unique way to pull back what it came from before. And that's the concept of injective. This shows that there's an injective map that goes from legit trees, labeled trees, to these strips. So this shows injectivity, which means that the number of labeled n-vertex trees is at most n to the power n minus 2. Well, in that case, we've got one more step to do, and then we're done. And the last step is to show this surjectivity. We need to show that if anyone just gave you any strip of numbers, where the numbers happen to be with values up from 1 up to n, where n is 2 more than the number of numbers you wrote. So I'm going to write remains to show. Given any strip of integers, let's call them positive integers. That way I don't have to worry about like 0 or less. Any strip of positive integers where each integer is less than or equal to the total number plus 2, right? That's what we just did here. We said that the number of vertices in the tree will be 2 more than the number of numbers in the strip. Given any such strip, there's a way, well, there's a tree. There's a labeled tree and vertex tree that would have given it. Does that make sense? Like, I just need to show that. And that's actually why I went and drew like some totally random thing. I made some random sequence of numbers as I opened this class. And that's like proof by randomness. You know, I just went and chose some random thing and there was a way and it worked. So that means that more likely than not, this theorem is true. And sort of like the empirical approach would be just do it for a whole bunch and it always works. Well, but let's go and prove that this is actually true, right? So what we need to do is we need to explain why this, why the thing that comes out at the end, which is this like interesting thing, it's a tree, and the tree is what would have given it. And if you think about what's going on here, we have to then show that first of all, we have to show that the decoding algorithm actually can be done on any arbitrary input, right? So I'll say to do this, need to do 2 things. The first is you need to show that if somebody gave you this strip and followed the rule called avoid the stuff to the left and avoid the stuff below to the right. So we need to show that the decoding rule even can be done. Okay? And I'll be more explicit in the next screen as I explain. Like, then to be done, it just means avoid the numbers to the left, avoid the numbers below and to the right. How do you know you even can find something that avoids them? We need to know that, so it can be done. And we also need to show that like the output, which is like we'll get this 2-row thing with n minus 1 columns, that output better be a tree. Show the resulting two by n minus 1 thing is the edge set of a tree. Okay, so I got to get these 2 things. And if I did these 2 things, then I'm done. Then I get the green thing. Because then somehow, no matter what strip I've got, it does come from a tree. Like that's this 2 by n minus 1 list of edges, and that's a tree. And if I just fed that tree in as input, it would be good. Okay? So how do I do this? Well, let's go and start to look at one. So if I'm anywhere in the process, I've got this 2 by n thing. 2 by n minus 1 thing. The last thing is kind of weird. We don't really worry about it. It's going to be the n thing that we throw inside. Like we're going to throw in n in the end. I'll just put that there. That's special. And now what I need to worry about is if I looked at some place in the middle of the process. Okay? So maybe I'm here. And I'm trying to fill in that thing there. How do I even know there's a choice? Well, what was the rule? The rule said that I have to avoid all the numbers here. And I also have to avoid all the numbers here out of the numbers from 1, 2, up to n minus 1. And the question is, how to know, or why, is there always at least one choice among the numbers 1, 2, up to n minus 1, avoiding the blue and green. How do I know I have a choice? I mean, like, if I have no numbers to choose from, I'm just dead. But why is there a number? Braden.
Well, you're choosing from the numbers 1 through n. And you only have n minus 1 numbers at max that you can't choose from. So there has to be at least one which is available.
Yeah, I want to be a little bit careful here. I was not very clear on my labeling. My n minus 1 is like the entire strip across, right? So actually, I think you just generalized one step, which was like, hey, why not just say choose at least one number among 1, 2, up to n, which just avoids and run the green thing all the way to the end. You could do that too. But the way I wrote it last time is I just ran it up to like 1 before the end. But actually what you said is also legit. But ultimately the same argument holds. The same argument is like, well, how much stuff is in the blue and the green? N minus 2 things. And I have n minus 1 things to choose from. So in the worst case, there's one choice. And there might be more than one choice. So the answer to this is easy. Easy. The blue plus green exclude only less than or equal to n minus 2 choices. That's it. Okay, so now this is the very satisfying thing of, well, you at least could decode it. Now the only question is, how do I know that what I get is a tree? Because that's a minor miracle, you know? It's like, well, what if I just followed this stupid algorithm called find the smallest number not in the blue and not in the green? Who's going to guarantee that's a tree? That's amazing. Like, that's actually an amazing fact. So I'll use the next screen to say, why is it a tree? Why is the result of decoding a tree? Well, now I need to think, what's the easiest? Ooh, Chris, you have some thought.
The tree generation algorithm.
The tree generation algorithm. You can be like, well, it seems like I'm building the thing one step at a time. And if you go look, let's look at an example here. It's like, well, I pulled this all off, and it would be really nice if we can say it looks like it comes from the tree generation algorithm. In fact, actually, that's a pretty good way of thinking of it, in the sense that every time I'm putting on something, if you think of like processing the edges one at a time, which is exactly what happened here, you sort of noticed it just kept growing in some way. We kept growing to a new thing. How to explain that? So if I was looking at this, it almost is like backwards in some sense. You know what I mean? It's like, maybe actually you could use your thing going the other way. I didn't even think about it that way. But I'm going to say, I have a different way of explaining it. I think that this sort of thing could probably be made to work, because we saw that the thing just kept growing forward and forward. I'm going to try to use something a bit more brain dead, because that's easier for me to check. It's easier for me to be like, well, what could make a tree? Could I show that it has n minus 1 vertices? And that it's like no cycles? That would also be an easy way. If I could just show there's like no cycles and there's n minus 1 edges, then I should be in good shape. And I'm not saying you're wrong, Chris, because all of these are like the same fact in the end. But I think it'll be a little bit easier if I just go and say n minus 1 edges and no cycles. Well, the n minus 1 edges at first looks kind of easy, because it's like, well, there's n minus 1 columns here. But the only catch is I need to worry a bit about, well, actually now I'm thinking, if you have less than or equal to n minus 1 edges and no cycles, that doesn't make a tree, actually. If I make a claim like, I have less than or equal to n minus 1 edges and no cycles, you could be like, haha, your graph has no edges. That's not a tree. So the issue is that I need to know that these are actually distinct, right? So I'm going to do that. So we're going to do 2 steps. So the first step is show you actually have n minus 1 edges. And the second thing is we'll show that no cycles. I see that there's another hand that went up. Andres?
I was just wondering, could it possibly be easier to show that any graph with cycles in it could not produce a legit proof or code?
So the issue is, so I like what you just said. What you said is like, show that if I had something with cycles, I wouldn't be able to proof or encode it. And the answer is, yeah, of course you can't, because like at some point you won't find any leaves left. Like if you think about what happens, if I start with an input called a big cycle, n vertex cycle, what's the first step of the proof or encoding? Find a leaf. No leaves, dead. Okay, so it is true, by the way, that if you have a graph with a cycle, the proof or encoding will fail at some point. That is actually true. However, that's not going to be enough to prove what we want. What we want is to show that if anyone said, hey, here's my strip of numbers, you need to show that there is a legit tree that made that. And that's not shown simply by saying that if I have a not tree, I can't do the process. Does that make sense?
Yeah.
I'm glad you asked that, by the way, because even when I prepare to teach this class, I always get slightly confused. So you're not the only one, right? So the way I try to articulate it is, if somebody gave you a strip of numbers, you better be darn sure that you could decode that, and it's like magic, it's a tree. And that's what you would have, if you put that tree in, now you get this thing. So I prefer to go this way with like n-1 edges and no cycles, because it's a little bit easier to me. It's like, how do I show there's no edges? Well, let's start. Sorry, no. How do I know there's n-1 edges? Well, what would it mean if there are not n-1 edges? If not, how could you screw up? Well, there's actually two possibilities. Oh no, now it's time for Roman numerals. If not, you got two possibilities. Two ways to break. Can someone give me one way to break? It could be a really easy way to show that, no, you won't break this way. Like, how, if I eventually constructed n-1 thing long, what's one way that I would be like, there aren't n-1 edges here, even though there's n-1 columns? Aha, Jack.
You have some like repeated column, I suppose.
Yeah, some repeated column. It's like, what if I had 3 and 7, and then you had another 3 and 7? That would be bad.
But I think we said that the top row should be all you.
Aha! Yes, yes, good. So the important thing is like, now I'm looking at this and I'm like, where did it break? Okay? So the thing I want to focus on is something weird happened right here on the second 3. On the second 3, it's like, who wrote a 3 there? That's a mistake. You should not have written a 3 there, because the rule of how you draw that 3 is you're supposed to avoid all the numbers to the left and below, but you didn't. You failed to avoid the numbers to the left because there's a 3 there. So this is just wrong. It's not possible during the decoding process to ever make this. Okay? So the important thing here is that at that 3, this is a mistake. Well, I'll call it not mistake. I'll call it, this is not decoding. Decoding will never make this. The great thing about math is you never make a mistake. So it's like, if we go and say, here's a procedure, we're going to prove something about it, we'll assume that you follow the procedure without making a mistake. So I'll say that the procedure can't put a number here that already appears before in the top row. Can't put number here that is already in top row. Okay, so that's how that doesn't break. And there was something else that's probably kind of trivial that I didn't mention before, which is called, I can't have like 3 above 3. But that's just because it's like, obviously the bottom row thing would break it. Is that clear to people? I'm just not writing that down. But it's like, you would never decode and get like a number directly above itself. That's just not possible. Okay, the other possibility is, can someone tell me what this would be? So I have an n-1 strip. How else could I screw up? Shania.
Oh, I was going to say something for the previous part.
Yeah.
I don't know if it's that important, but like, if you have like 3, 7, you can also show that later on you can't have like 7, 3.
I want that right now. Okay, so that's the one I want. Okay, the other way you break is this one. There's 2 ways that you repeat an edge. Now, could you tell me why this can't happen?
Because when you're building like that top ring,
Mm-hmm.
you know that if you have a 3 at the bottom later on, you can't have the 3 at the top. That's like 2 of them.
So that one's screwed up. So what you're saying is like, remember we build the top, right? So as you build the top, it's like, nope, I'm not allowed to go and build this thing here because the 3 appeared later there too. Okay, so that's what happened here. So good, that deals with this. So in the second one, this thing, you failed to avoid something else. You failed to avoid the 3, which is below to the right. Actually, now I'm also realizing I probably should have just stated the whole algorithm as go all the way to the end, which is what Braden was doing. I had been explaining it before of go all the way up to 1 short of the end and avoid all the numbers, find something in 1, 2, 3 up to n-1. But you can actually restate the whole thing in terms of go all the way to the end and just take the things out of 1, 2, 3 up to n. I actually think that would be easier from point of view of logically reasoning about this algorithm. So I'm actually going to amend that. I'm going to say, actually, oops, wrong pen. Actually, better to use the algorithm, choose from this 1, 2 up until n, except for anything to the left on the top row and anything below and to the right, including final n. Okay? So it's like, it's the same thing actually. Like this thing that I just wrote is exactly the same thing as up there because the final thing is n. So there's actually no change. But that makes it easier for us to go and argue here because we want to make sure that in our analysis it includes the possibility of the last column as well. So what we find out here in this particular picture is that you know since must avoid below right. I'll just call it that way. Okay? So now we know that we really have to have n minus 1 edges. Now the only tricky part is, what if there's a cycle? How could there be a cycle? Why no cycle? So now this is the one where we have to think a little bit. What would a cycle look like? Suppose there's a cycle. And the way I want to think about this is that the cycle is made up of edges. Okay, so we've got this big n minus 1 across, 2 up and down. Okay, and the cycle is made of edges. So there's a bunch of these edges that contribute to the cycle. I'm just like marking them. They could even be next to each other, or they can be far apart. Let's pretend that the cycle uses these edges. Cycle uses these edges. Now my claim is you can use this to show that there's something fishy going on. And this is an example of an extremal type of argument. I'll just be like, there's some label here, call it x. I claim there's a little bit of a problem if you go and look at this thing. Suppose there is a cycle using all of these edges, and x happens to be a vertex inside the cycle, because I actually chose the first one. The important thing about the x is this is the first edge, leftmost edge in the cycle. Leftmost in the in this table from the cycle, right? So the cycle is made up of some number of edges. I went and found the leftmost edge. I went and looked at the top thing, called it x, and I claimed that we can use this to get some kind of a contradiction. There's a cycle now. There's an x. We're supposing that this made something in the graph. Actually, in this example, the cycle only has 4 edges. So let's do this. How can I show that something is bad? I want to say that the fact that these 4 edges form a cycle, it needs to give me a contradiction, and it's going to be something to do with this x. Oh, another person, Cindy.
The x is connected to the thing below it. It's also connected to another thing since it's in the cycle. So it has to appear again to the right somewhere, but it can't.
Aha! X must appear again. You're right on. X has to be appearing again. And the issue is it can't. The reason it can't is because, well, what do you mean appear again? Appear on the top or appear on the bottom? You'll lose both ways, right? Why can't it appear on the top? Well, we went over that before. We already saw that in the previous screen, that you can't have 2 same things on the top because, well, then the second appearance of it screwed up. You can't have X appear again on top because I'll call it 1. There's actually a reason why I did the previous example. I'm claiming that this thing about the n minus 1 edges is actually basically the same argument. You see, because if it appears again on top, well, because 1, well, look back one screen. There was this 1 of the same number appearing twice on top. The second one screwed up. Otherwise, appears again on the bottom. And you can't have x appear again on the bottom because of the 2. The 2 was like if I have an x up there and I have an x down there, then the one that was up there, the first one that was up there, shouldn't be there because it was supposed to avoid everything below and to the right. Did that make sense? I'm just showing that somehow that 1 and 2 actually are the same logic you use here. And in fact, that should make sense because, you know, actually getting 2 edges, if you really had 2 edges, that's sort of like a cycle, going and coming back. So this notion of a cycle is just generalizing the idea that you could have gone around. And by the way, that's why we chose the first x. Because, like, you see, you wouldn't immediately get the contradiction if I went and grabbed something over there. If I went and grabbed the number up there, I call that y, maybe y appears down here. I mean, that's possibly okay. Like a y down here and a y up there diagonally in this kind of positive slope way, if I think of it as like a plot. Like I could have the same 2 numbers appear, one down there and one up to the right. That's totally legit. And so that's why I did something very sneaky here, which is I said the one that is the problem is the number that's in the top left. That's the example of how these arguments go. That shows there's no cycle. I saw there were a few people who had some comments or I don't know if there are questions or comments. If you still have a question, because I know some people are trying to answer the question, if you have still a question, please feel free to ask again in the chat and I'll raise hand again in the chat and I'll call on you. But meanwhile, I'm going to say this is pretty cool because what we have just done is we have just gone and showed that there will be n minus 1 edges and there will be no cycles. So it's a tree. So that means that if you start with any old thing and decode it, magically, that thing will correspond to this nice n minus 1 wide and 2 up and down. And when you turn those into legitimate edges and you draw it, bang, it's a tree. And that's cool. Like the idea that you could say that every one of those strips decodes is not something that you'd expect. But it does. So this actually finishes the proof now. This proves that the number of trees is n to the n minus 2. And it looks like the proof was kind of long, but the way to think about it is it's sort of like we did everything that we had to do in order for things to make sense. We were always saying, well, it's like a Sudoku. If I have this number down on the bottom, what could be on top? And eventually we came down to the question of, well, how do you know you can always decode, which is what we did today. Any questions about this? If not, we're done with the proof of codes. Okay, let's go on. And now let's talk a little bit about how many unlabeled trees are there. This is a quick thing. I'll just say a really quick thing about unlabeled trees. How about the number of unlabeled trees? Now that was a bad thing. We got a bunch of numbers and they weren't nice, right? Like we saw the nice numbers for the number of labeled trees, got super excited, and then we proved something. For the unlabeled trees, we got weird numbers. Unfortunately, I think nobody knows a nice formula for the actual number, but there's a way you can approximate. And for example, you know, how many should there be? Remember, the number of labeled trees is n to the n minus 2, okay? So the number of labeled is equal to n to the n minus 2. That's bigger than normal exponential. Normal exponential is just like 5 to the power n or 100 to the power n. But this is n to the power n-ish. And the base of the exponent is also getting big. If you remember, I said this was sort of like squiggle, 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 squiggle. It was sort of like exponential of n times the log of n. Something like this, okay? And that's because the first n that you raise to the n minus 2, the first n is like 2 to the power log base 2 of n. And then you use exponent rules. But it turns out the number of unlabeled trees is only exponential. So you can actually go and prove that the number of unlabeled trees has a bound which is significantly different from this one. This is super exponential. You can show it's only exponential. So that means there's a lot less labeled trees, which one might expect because, you have a lot of the unlabeled trees are really the same. Sorry, a lot of the labeled trees are really the same unlabeled tree. But how would you do this? To do this, we need to find an interesting way to encode an unlabeled tree. We are going to show a bound saying we'll prove that this number is less than or equal to something. Okay, it'll be something. It'll actually be something to the power n. That's what we'll show. Ish. It'll be n-ish. We'll see soon. But now the point is, if I want to do this, I only need to show that there's a way to start from any unlabeled tree, make some kind of a code, and then I just need to say that I never make the same code with two different trees. Just need an encoding algorithm that never makes the same code twice for different trees. That never makes the same code for different trees. And I mean, that just is injective, right? That's the same thing we had before. That just means it's injective. And somehow the encoding algorithm needs to be such that the number of things in it is at most some exponential in n. Okay. But now at this point, you're like, wait a second, how are you going to encode this? The vertices have no names, right? Like everything we did before, we had names. So here's something that the first time I ever learned it was from the textbook that was suggested for this class, which is this Lovas, Pelikan, and Vestergombe book about discrete mathematics, which we actually haven't been following, but maybe vaguely following. I will say a fun fact, if you are at CMU, which I guess all of you are, the book you can actually get for free. I think I found out that it's like site licensed by CMU. If you go like from your CMU dorm to a certain webpage, you can download the whole book. But we don't actually follow the book closely. Nevertheless, the book taught me something neat when I read it, which is, hey, here's an encoding algorithm for an unlabeled tree. That's reasonable. That's an unlabeled tree, okay? Let me tell you how to encode this. And I will say that whoever thought of this is quite clever. It's called hire an ant. Okay, so what's the ant going to do? It's going to go crawl around the outside of the tree. From anywhere. It can start from anywhere. Crawling around the outside of the tree. Start anywhere. Okay, now the important thing is that, another important thing. Choose one of the vertices to be the root. So somebody is going to be the root. Who's the root? This one. Okay, start anywhere, choose any root. Choose any vertex to be the root. Now, we're not saying there's only one way to encode. In fact, there will be many ways to encode, but we're just proving an upper bound, a less than or equal to. When you're proving a less than or equal to, it's okay that you say, well, here's a tree, it could be encoded in that way or that way or that way, as long as I make sure that I don't ever have two different trees encoding the same way, I'm good. All right, so hire an ant, start anywhere, choose any vertex to be the root, and now start like crawling around. Crawl around the outside. Okay, now as the ant's going to remember for each of its moves, did it get closer to the root or farther from the root? So in particular, the first thing, I'll call it a minus, because it got closer to the root. Does that make sense? So the first move that they made, the ant was going closer to the root. Was going closer to the root, right? A minus if go toward root, and I guess there would be plus if you go away from the root. Well, why is this interesting? Oh, wait, someone wants to guess. Chris, maybe it's too late, I already said something. But yeah, what do you want to say?
I was going to guess that the algorithm is something like, you have another strip, and then for each vertice, or for every unlabeled vertice, you say how many edges it has, and then the cumulative has to add up to 2n.
Ah, so that's another way. So you're thinking of like some other way you could try to do the encoding where you're saying, I'm going to have all these vertices, and under the vertices, I'm going to write like some numbers of some form, which is something to do with like my degreeness. Is that right? So actually, that's a pretty interesting idea. One idea would be called, I have an unlabeled tree. Pick up a root, dangle it down or something, and it's like, just keep track of how many things do I have dangling. Like in my first thing, do I have like 3? And from those 3, how many do I have? So the answer is you can do that. You can probably actually get an even better bound that way. But the reason I'm doing this way is because if you do it that way, you're writing a sequence, you're writing a strip, and your things in the strip are numbers that could get big, meaning like they could go up to n. And then the problem is if somebody tells you there's a strip of up to n things, where each of the numbers could be up to n, you're back in the world of n to the n. I want to get a bound which is going to be a number which has nothing to do with n, a constant to the n. And that's just why, like, by the way, what you described is if you want to really nail this, you can actually go and start to do it that way. But this is just quickly showing that it's exponential. Okay? And that's why this is the funny ant approach. It's not as good, actually. But so the ant's going to go around, like, with some minuses. And then the next step the ant takes is a plus. Just want to emphasize, the second one's a plus because that's going away from the root, according to the tree. Then the ant goes around with a minus. And then the ant, that's a minus. And then the next one is the ant goes down with another minus. Is this making sense? The ant's going to go all the way around the tree. Plus, minus, or whatever. Go all the way around. Well, we'll write a strip. Because at some point you go go all the way around, and finally you come back with a plus. Does that make sense? Eventually you come back with a plus. So what you end up getting is you get a strip. And the strip has minuses and pluses. Minus, plus, minus, minus, and then plus, and then it'll be plus again, and so on. And the final thing is a plus. Why is this interesting? Well, first of all, how many things are in this strip? If there are n vertices, how wide is the strip in terms of n? Braden.
It should be 2n because the ant's going to walk along each edge or up 2n minus.
I'll just put that in. It's about 2n. Yeah. It's 2n minus 1 because every edge you hit twice. It's just like twice the number of edges. Okay, but here's the nice thing. Guess what? Each thing's a plus or a minus. So I just get 2 to the power 2n minus 1, which I can actually write as 4 to the n, if I just want some bound, okay? So what I just did here is that the number of strips is, well, less than or equal to 2 to the twice of n minus 1, which is definitely less than 2 to the 2n, and that's 4 to the n. We're just showing some exponential bound. But that's just showing like, okay, yeah, sure, I could do this plus and minus. The key part is, how do you decode this thing? Like, how do you know that if somebody gave you some plus minus thing that was legitimately from a tree, promising it's from a tree, how do you know you can get back the original tree? Well, you just play the ant. So the point is like, if you wanted to get this back, so how do you decode? Well, all you do is you just say, if I have a plus, right? So I'm just like an ant. And if I have a plus, sorry, it was a minus first. If I have a minus, I guess, actually to decode, I'll draw it this way. I'll say that the root is on the top. I start somewhere, and I get a minus, so I'm going to go up. Does that make sense? And then I have a plus. Okay, if there's a plus, then I'm going to go back down. Yeah, wait a second. So minus is up, a plus is back down, but remember, this is on the outside of a tree. So, okay, so we're going plus, which is back down. And then it's minus again. Minus is going to tell you that you went back up this way. Is this making sense to people? I'm just showing how you would pull this off. Because you start off with a minus. I'm just looking at this particular thing. Start off with a minus, and then you go with a plus. But then now, when you do the minus, you're crawling around a tree. So you go back around with the minus. And then there's another minus, so you go back up. And then now suddenly you get a plus. So the plus tells you to go back down again. And then you get another plus, and the plus is telling you to go back down again. And is it clear to people that this is just giving exactly one way that you would crawl around a tree, like this? And the point is, if you do this, well, you'll get a tree. And since there was only one tree you can get in this way, if you can see, whenever I'm making these decisions, I don't have a choice. And as I'm building this tree, because I'm crawling around the outside of it, so as I'm building this tree, I don't have any choice as I keep building this. So what I end up getting is better have been the original tree. So that's it. So the point is, like ants crawling around trees, if they just keep track of the way that they crawled, you only have one way of getting that tree back from the beginning. And so this shows that the number of unlabeled trees is at most 4 to that. With that, that finishes this section. And we will continue next time with a totally different topic in graph theory. We will have 2 lectures on it, I think, before the exam. And then, well, then we'll continue on. Okay? I'll close out the YouTube.